In this video, we're going to talk about regression and regression lines. We do regression and regression lines if there is a significance in the correlation cofactor. Remember that in previous videos we discussed working with the hypothesis test for rho when it was equal to 0 and the alternative hypothesis being rho not equal to 0. Remember that rho is the population correlation coefficient, and so we have rho is equal to the population correlation coefficient, whereas r is the sample correlation coefficient. Okay, and in order to know that there is a significance to the correlation coefficient, we want to make sure that we have rejected our null hypothesis, meaning that there is a difference between rho and 0. Our correlation coefficient is further away from 0, because remember that correlation coefficients can be between -1 and 1. And so we want them to be as close to the 1 as possible. The closer to 1 as possible, the more significant they are. So we do the hypothesis testing, and if we reject our null hypothesis, that means that there is significance for the correlation coefficient. If there's not a significance for the correlation coefficient, a regression line should not be done. Sometimes it is just so that we can make predictions, but it's not very accurate predictions that we do. So the first thing that you always want to do is check for significance of your correlation coefficient. So always check for the significance of your correlation coefficient, and that is, do we reject our null hypothesis or not? Okay, and the whole purpose of this is so that we can create the best fit line, what we call a regression line. And so when we go back and look at a scatter plot, remember, here's my x, here's my y, and let's just say I'm going to put some random points on there for right now. Okay. And what I want to do is I want to see what the best fit line for this is. And in order to do that, I've got to find what the value is. And so we're going to come in here and we're going to calculate, based on our information, a line that will best fit this data. And then we look at items. This is what we call our regression line, and it's also considered our predictor line. Okay? Remember that lines are always going to have a slope and a y-intercept. And the equation of this line is going to look like y prime is equal to a plus bx, where your b is equal to your slope and your a is your intercept for your y prime, meaning it's where this line is going to hit the y-axis. Okay, and remember that slope is how far we rise over run, how quickly it goes up or goes down. So in this case we would have a positive slope because it's going up. And so we're going to be calculating how to get this line. One thing that we also look at is something called the residual, or also known as the predicted error. The predicted error. What this is it is the difference between this point and the point on the line. So this right here is the residual. It's the difference between the actual value of y and the predicted value of y. And we use this to determine this best fit regression and how it describes this line. So let's see how we can figure out this equation. What we need to find is our a and our b. Remember that y prime and x are going to be staying the same. Y prime is strictly the predicted value. Predicted value for y. Okay. So let's look at how we can calculate these. And if we look at first our a, that is going to be calculated by the sum of the y's times the sum of the x squareds minus the sum of the x's times the sum of the x times y's, all divided by n times the sum of x squared minus the sum of your x's and that value squared. Now if you recall, we actually already found all of these sums when we found the correlation coefficient, where we drew out the table. And we're going to look at that again. And so if I rewrite this based on those columns that we were looking at earlier, that is the sum of column B times the sum of column D minus the sum of column A times the sum of column C divided by n, and remember n is how many pairs you have, times the sum of column D minus the sum of column A squared. And this will give us our A value, which is our y-intercept. Let's look at how we would calculate our B, our slope. So remember that A is our y prime intercept, and that B is going to be our slope. So B is going to be equal to n times the sum of x times y minus the sum of x times the sum of y divided by n times the sum of the x's x values squared minus the sum of the x's and that value squared. Okay. The denominators in A and B are the exact same. So this denominator and this denominator are the exact same. And so when I put this in column format, it's going to be n times the sum of column C minus the sum of column A times the sum of column B divided by n times the sum of column D minus the sum of column A squared. And so you can see that my denominators are the exact same. It's the numerators that are going to change between my y-intercept and my slope. We want to make sure that whenever we're doing this, we always round both of these to 3 decimals. Okay, this is the standard procedure for rounding of the regression line. So let's look at an example. We're going to go back to the example with the deaths from lightning. Now let me make one statement. When we did the correlation coefficient and we did the hypothesis testing for it, we did not reject the null hypothesis. Therefore, in all reality, a regression line should not be done for this example because it was not a strong enough or significant correlation coefficient. But a lot of times, again, we do go ahead and do the correlation coefficient and the regression line so that we can make predictions. But just know that most of the time when you do not reject the null hypothesis, you should not be doing the regression line because the regression line is going to be extremely off. Okay? So let me go ahead and refresh your memory that we had deaths from under a tree and we had other types of deaths. This was our X and this was our Y. Okay. And we had 8 with 21, 5 with 29, 13 with 34, 6 with 36, 11 with 40, 9 with 37, 6 with 26. And so what we're going to do is we are going to calculate the same columns that we did when we needed to find the correlation coefficient. And so we're going to have column A, column B, column C, column D, and column E. And remember that column A was our X value, column B was just our Y value, column C was X times Y, column D was our X squared, and column E was our Y squared. And so when we go through here and put in our values, and I'm going to go ahead and put in the X and Y first. Make sure that you're still lining them up with their pairs. So in other words, the 8 with the 21, the 5 with the 29, because it's going to be important for column C that we have. Okay? And I'm going to go ahead and draw dividers for my columns, and then remember that we are going to sum it up at the end. Okay? And so values here, if we multiply 8 times 21, we'll get 161. And I'm filling in the other numbers because we have done this in a previous video. Then my X squared is going to be 8 times 8, which is 64. And then the other values for that. And then my Y squared is 21 times 21, which is 441. And then my other values where I'm taking Y and multiplying it by itself. So like this one would be 40 times 40, 37 times 37, and 26 times 26. Okay? And then we want to get the sum of each of these columns. So I'm going to add up each of these columns, and I'm going to get a value, and I get 58, 223, 1,900, 532, 7,379. And then I want to count to know what my n is. N is basically the number of rows that I have, or the number of pairs. I've got 1, 2, 3, 4, 5, 6, 7 pairs. So my n is 7. And so these are the numbers, these sum numbers, and this n is what I need to find my A and my B. So let's start with A. And A was the column A times column D minus column A times column C divided by n times column D minus column A squared. So A is equal to 58 times 532 minus 58 times 1,900 divided by 7 times 532 minus 58 squared. Okay? And I'm going to do all the multiplication parts first, and then I'll do the subtractions. And so I'm going to get A is equal to 58 times 532 is 118,636. Let me scroll down just a little bit. And then 58 times 1900 is going to be 110,200. 7 times 532 is 3,724. 58 squared, which is 58 times 58, is 3,364. Now I'm going to do each individual subtraction. So that is 118,636 minus 110,200. That's going to be 8,436. And then 3,724 minus 3,364 is 360. Do that division, and I'm going to round to 3 decimal places. That's going to be 23 and 433 thousandths. This is my A value. And I get to do the same thing for my B value. Recall that B was N times column C minus column A times column B divided by N times column D minus column A squared. So I have 7 times 1,900 minus 58 times 223 divided by 7 times 523 minus 58 squared. Again, I'm going to do the multiplication first. You can put this all in your calculator at one time. You just have to be really careful. If you do, I would put the numerator in the calculator, get a single answer, put the denominator in the calculator, get a single answer, and then do your division. If you put it all in at once, you've got to really pay attention and put parentheses around the entire numerator, around the entire denominator. Otherwise, your calculator actually does order of operations in a way that we don't always see. And so if we don't put the parentheses in the proper places in our calculator, it's going to really mess up your numbers. Okay? So you might need to practice quite a bit with your calculator to see if you're getting these same numbers at the very end. And if you're not, you might need to take it a little bit step by step or something along that nature. Okay, so where I did 7 times 1,900, I got 13,300. When I did 58 times 223, I got 12,934. And then notice my denominator again is the exact same, so I should get 3,724 minus 3,364. Then I'm going to do the subtraction. So 13,300 minus 12,934 is going to give me 366. And my denominator again is the exact same of 360. I'm going to do that division and I'm going to round to 3 decimal places. Remember to use correct rounding rules. And you get 1 and 17 thousandths. Now that we have our A and our B, what we can do is we can put that into our equation of y prime is equal to A plus bx. So y prime is equal to 23 and 433 thousandths plus 1 and 17 thousandths times x. This equation is used to make predictions now, because remember that our x value is the number of deaths under a tree. And so we can make predictions based on the number of deaths per tree for that particular year, how many other deaths there might have been. And that's the whole purpose of this equation, is to make those predictions. For example, if we want to know how many other deaths occurred during a year when there, let me rewrite that. We'll say when there were 7 deaths under a tree. Okay. So that means that this is your x value, and we want to know the y value. So we're going to plug this number in for x here, and we're going to solve. So let's look at how we would do that. And so we would have that y prime is equal to 23 and 433 thousandths plus 1 and 17 thousandths times our 7, because that's the number of deaths under a tree. All I've done is plugged in that number of deaths under a tree in for my x value. Then I'm going to solve. So I need to multiply first, and then I'll do the addition. So I get y prime is equal to 23 and 433 thousandths. And if I take 7 times 1 and 17 thousandths, I'm going to get 7 and 119 thousandths. And then I'm going to add the 23 and 433 thousandths, and I will get 30 and 552 thousandths. So we get this decimal. We have to think about it. Can we have a partial number of other types of deaths? No, so we're going to round. And we're going to round using normal rounding rules. So there were about 31 other types of deaths in a year when there were 7 deaths under a tree. So we now know that there were approximately 31 deaths, other types of deaths, when there were 7 deaths under a tree. This equation, the y prime is equal to a plus bx for whatever problem you're working with, this equation is used to make predictions about the population. Now you may have had in your original data set a year that had 7 deaths under a tree, but if we want to make a prediction about the population, we're going to plug that 7 in here and find the predicted value, because that is about the actual population. Remember, all of our data right now is coming from a sample, and so we need to expand it and make that prediction back onto the population. Okay, so do some of the practices with the regressions, with the calculations and everything. Try some of those, and if you have questions, please feel free to ask me.